When we have the sketch of part of a function, we've already seen a way that we can work out how to draw the sketch of closely related functions under some circumstances. In the cases we've looked at, we can see how to translate the graph either parallel to the x or y axis to get the graph of a closely associated function. We're now going to look at a similar situation. If we know what the graph of y equals f of x looks like, then what would the graph of y equals f of x divided by k look like, where k is any constant? Well, this again is a slightly abstract and difficult to visualize situation. Let's go back and look at our example for the particular case where k is 2. So here is our sketch of y equals f of x. As before, we don't really know what the equation of this curve is, and that's not really important. We just know this is what the curve looks like. And what we need to try and do is to draw the graph of y equals f of x over 2. So if we have a particular x value, let's start by looking at the point right at the end of this curve here. That's got coordinates negative 4, 5. Well, if I want to draw the graph of y equals f of x divided by 2, I can see from this the point that I would have to plot above an x coordinate of negative 8, because the y value that would go with that would be the y value we would get by looking at the original function of negative 8 divided by 2. Oh, that's exactly this point here. And the value of the function when I've got an x coordinate of negative 4 was 5. So therefore we need to plot a y coordinate of 5 above this x coordinate of negative 8 on our new sketch. Similarly, if I want to know what to plot above negative 6 on the new curve, well, on the old curve I would have to divide the negative 6 by 2, giving me negative 3. What was the value plotted above negative 3 on the old curve? It was 2, so I have to plot that y value of 2 above negative 6. I can similarly continue for different x values. In every case, the y value we would have to plot is the value of the original function for that x coordinate divided by 2. So now we can see what the curve through all these points would look like. Let's just remove the coordinates of those points to make it a little easier to see. And the curve we have looks like this. Now we can see how we've got that curve from the original one. The original curve has been stretched by a scale factor of 2 parallel to the x-axis while leaving the y-axis invariant. In other words, if we look at this point, it's moved twice as far away from the y-axis. If we look at where this point is, it's moved twice as far away from the y-axis. This point's moved twice as far away. This point has moved twice as far away. The point 0, 0 has stayed in the same place because all the stretching is going parallel to the x-axis but with respect to a fixed y-axis. So this suggests a general rule. If we've got our axes, then going from the graph of y equals f of x to the graph of y equals f of x divided by k would be a stretch parallel to the x-axis, leaving the y-axis invariant, with a scale factor of k. Let's check that for other values of k. Let's tidy up the display so it's easier to see. And also let's include something where we can see the value of k. Let's put that down to 1. So if k is 1, of course the curves y equals f of x and y equals f of x divided by k will be the same. X divided by k will just be x. But now if we let k increase, then the image function is stretched away from the y-axis parallel to the x-axis. It doesn't take long before we can't even fit it on our display anymore. Let's just stretch this display a bit so it's easier to see. I've just scaled down the x-axis a bit. Let's see what happens as our k increases. Indeed, we're stretching further and further away from the y-axis parallel to the x-axis. So we have a third transformation rule to go with our two translation rules. Now, if we take the graph of y equals f of x and replace the x with x over k, so now we're sketching the graph of y equals f of x over k, then the transformation that goes with this is a stretch parallel to the x-axis by a scale factor of k. Let's now investigate a very similar situation. If we know what the graph of y equals f of x looks like, then what would the graph of y equals k times f of x looks like? It's a very similar thing to our previous one, but here the multiplication factor, the k, is outside the function of x rather than being inside it. Let us once again investigate this using our standard example. Well, if I know that this point above negative 4 has coordinates negative 4, 5, in other words f of negative 4 is 5, what would I plot above negative 4 for this new function? What I would have to do is find the value of f of x for this value of x, so for negative 4 the value of f of x is 5. Then I would have to multiply it by 2 to get 10, and that is the point that I would have to plot above negative 4. Well, I think the pattern here is going to be quite clear. For every value of x, we find the value of the original function and we double it. We'll get these points. And now if we remove those coordinates to make it a little easier to see, and we join those points up, the curve we get will be this one. So how did we get from the original graph y equals f of x to y equals 2 times f of x? Again, we've got some stretching, but this time the stretching is parallel to the y-axis. We're stretching up and down with respect to a fixed x-axis. And again, the scale factor appears to be this 2. This suggests to us this general rule, that if we are doing this transformation from y equals f of x to y equals k times f of x, then this time we have a stretch parallel to the y-axis, leaving the x-axis invariant, which has a scale factor of k. Again, let's investigate that for various different values of k. If we tidy up our original diagram so it's easier to see, if we set k equal to 1 so the curves will coincide, let's see what happens as we vary k from 1, making it larger. Yes, as it gets larger, the curve stretches and stretches parallel to the y-axis. Very quickly it's difficult to see that curve, so let's again do a little shift of the y-axis to squeeze a bit more onto the screen. Yes, we can see that that seems to be exactly what we have found. However, there's a more convenient way to look at the algebraic change we've done to fit in with that geometric change. If, instead of writing y is k times f of x, we instead divide through by k to get y over k is f of x, then you can see that the change we've actually made is to go from the original equation with a y in to a new equation with a y over k in its place. This suggests the following form for what we have done. If we replace y with y over k, then we have a stretch parallel to the y-axis by a scale factor of k. Once again, by rewriting things in this way, these two new rules are really just one rule, which can be expressed either in terms of x or in terms of y. Now, one thing we have yet to consider is what happens if the value of k is less than 1. We were always considering values of k greater than 1, which gave us a scale factor where things got further away either from the x or y axis. Let's go back to the y equals f of x over k. Now if k increased from 1, where the curves coincide, to 2, then we did indeed have a stretch of scale factor k up to, in this case, 2. Now let's see what happens if we let k get smaller and smaller again. When it goes smaller than 1, the curve gets closer and closer to the axes. In other words, we still really have a stretch of scale factor k, but when, for example, k is a half, a stretch of scale factor a half really gets things closer to the axes. So the rule we have got will work for any value of k, although so far we've only considered values greater or equal to 0. We'll deal with negative values at a future date. Notice that this also applies for our stretches parallel to the y-axis. If the scale factor becomes less than 1, then again we are squashing, if you like, closer to the axis, but we would still call it a scale with a scale factor which just happens to be less than 1. Let's illustrate this with an example which may look a little familiar to you if you've watched the video about translations. The diagram shows a sketch of part of the curve with equation y equals f of x. The curve intersects the x-axis at A and C and has a minimum point at B. On the same diagram, sketch the curve with equations. Firstly, y is 2f of x, and then y is f of 2x. We should show the coordinates of the images of the points A, B, and C on your sketches. Just for clarity, because it's a little difficult to see on that page, here is that curve. We can see that it crosses the x-axis at negative 6, 0 and 9, 0 and has a minimum point at negative 1, 6. Well, before we see the effects on that curve, let's see if we can work out what we think should be happening. Firstly, if we want to go from y is f of x to y is 2 lots of f of x, it might be better for us to write this new version as y divided by 2 is f of x. Then our rules predict that what we will have is a stretch parallel to the y-axis of scale factor 2. So for those key points, all of their x coordinates should stay the same and their y coordinates should become twice as big as they are. So as well as the original curve, we can display the new curve, which at the moment will be overlaid on the original one, because at the moment we just have a value of k of 1. We want to see what happens when that changes to 2. And we can also see the images of the 3 points A, B, and C. We'll call them A', B', C'. So our prediction is that everything will scale up parallel to the y-axis with a scale factor of 2. Let's increase k from 1 to 2. That's exactly what is happening. And we can see that the point A has stayed in the same place because its x-coordinate is still negative 6 and its y-coordinate has been doubled from 0 to 0. And the same thing will happen to C. But the point B, which was originally at negative 1, negative 6, has now moved down to negative 1, negative 12. Now what do we predict is going to happen if we go from the graph of y is f of x to the graph of y is f of 2x? Well, this is not the form that we need to understand what is going to happen. We need to see x replaced by x divided by something. But if we rewrite this, instead of 2 times x as x divided by a half, that is the same as 2x. Let's just check that. If I take x and divide it by a half, that is the same thing as multiplying it by the fraction a half flipped over. So yes, that is the same thing as 2x. Now we can predict that what should happen is a stretch. This time it should be parallel to the x-axis, and it should be of a scale factor of 1/2. So everything should get closer to the y-axis. Let's see if this is borne out. So we have two curves superimposed at the moment because the value of k is 1. So they will both be in the same place, and the original points A, B, C and A', B', C' will be in the same place. Now let's increase k from 1 to 2. So we end up with the curve y equals f of 2x. Yes, as it increases, everything is getting closer to the y-axis, and here is the curve that we needed. It has been stretched by a scale factor of 1/2. The point A, which was at negative 6, 0, is now at negative 3, 0. The point B, which was at negative 1, negative 6, is now at negative 1/2, negative 6. The point C, which was at 9, 0, is now at 4.5, 0. In summary then, we have two stretch rules to go along with our two translation rules. It's worth pointing out again that this is not the way that this is usually expressed. In most places you'll see this explained. The first of our stretch rules is usually explained by saying if you go from y equals f of x to y equals f of kx, then what you have is a stretch, and it is parallel to the x-axis, but it's usually expressed as being of a scale factor of 1 over k. Now that is equivalent to what we've done, but I don't know, not quite as easy to remember and fit in with the second rule. The second rule is usually expressed as going from y equals f of x to y is k times f of x. And this would be a stretch. It is parallel to the y-axis, but this time it would be a scale factor of k. I can see why people do it this way. The transformations algebraically are easier to understand. However, the two rules now look a bit different from each other, and I very much like this way of doing it, where we have replace x with x over k or y with y over k, because the transformation rules are exactly the same. It's always a stretch. It's always parallel to whichever is the axis which corresponds to the symbol that's been replaced, and it's always a scale factor of k.